regret I regret that I'm having certain health problems which do interfere to some extent with travel, but I'm very pleased that you allow me to appear via Zoom. The title of my talk is The Mystery of Two-Color Partitions with Distinct Parts. I want to pay special tribute to my co-author, Mohammed El-Bahrawi, who's really the instigator of the series of papers that we've written related to this topic. And I thank him very much for inviting me into his research program. So, of course, a good mystery starts with, this is neither a picture of me nor Bahrawi, but Basil Rathbone as Sherlock Holmes. So the mystery will develop slowly as the talk develops. So two-colored partitions have been studied extensively. And so these are the two-color partitions with distinct parts. So I denote that by PD of N. This symbol minus Q, Q infinity, this is the standard Q Pockhammer symbol. 1 plus Q, 1 plus Q squared, 1 plus Q cubed, etc. That infinite product squared. And this is sequence A022567 in the OEIS. Krishna, who just spoke, and the late Basil Gordon consider a more general case of this, where they introduce parameters A and B, and this is in their extensive and beautiful development of weighted words, which leads to a proof of Schur's theorem, Gold's theorem, and many other results in the theory of partitions. Part of the 26-year hiatus that Krishna referred to between his earlier work and the work he was presenting today. So we begin with the period theorem of Grabner and Nothmacher from 2006, which David Newman and I independently discovered more than a decade later, which is that the number of these two-color partitions of N is equal to this sigma mex of N, where sigma mex of N is the sum over all partitions of N of the minimal excludant of each partition. The minimal excludant is the smallest positive integer that's not in a given partition. So let me make clear what's going on here. So when N equals 4, here are the 5 partitions of 4. So the first missing part in the partition of 4 is 1. In 3 plus 1, the first missing part is 2. 2 plus 2, the missing part's 1. 2 plus 1 plus 1. The first missing part is 3. And then when there are 4 ones, it's 2. And if you add that column up, you get 9. So to represent colored parts, I put on subscripts R for red and B for blue. And so I've now written down the 9 partitions of 4 into 2 colors with distinct parts. By distinct parts, I mean you can have, say, you have 2R plus 2B. They are distinct either in color or in numerical value. And so how does one prove this? Well, first you consider how you generate the minimal excludant generating function. And so in order to do that, we look at where N is the missing part in the partition. And so you see in this sum, in the nth term, you have to have the numbers 1, 2, 3 up to N minus 1. Z is keeping track of the excludant, so you put in C to the N, and every part is then possibly multiplied, or appears multiple times from the infinite product in the denominator, where you exclude M equal to N, and this should be 1 minus Q to the M, I'm sorry, not 1 minus Q to the N. Anyway, once you sum up the arithmetic progression on the exponent of Q and take the full infinite product out, just making sure that you cancel out 1 minus Q to the N, this is the M of Z and Q generating function. And in order to add up the sum of all of minimal excludants, you need to differentiate with respect to Z and set Z equal to 1. And so you wind up with this as the generating function for the sigma mex of n. And now you just separate these two terms up vis-a-vis the 1 minus q to the m, and you get those two series shifting the index of summation in the second sum, and you see that there's a great deal of cancellation occurs. Indeed, we could combinatorially directly prove that this last expression is the generating function for sigma mex, because you see q to the m plus 1 choose 2 could be written as q to the 1 plus 2 plus 3 plus m. And so the first m terms there will include a partition whose first missing part is n, but not will be missing from that point on, so that this is, you can jump directly from the top line here to the bottom line combinatorially. But once you get to there, then you need Gauss's famous theorem, which is the infinite product representation of this triangular number series. And then just a few cancellations, and you're back to the generating function for PD of n, and that proves the theorem. Our initial focus is going to be on a refinement of this idea where we have only one color as the smallest part. So we're saying that S1 of n is the number of two color partitions of n into distinct parts with smallest part red, so that the previous case, the smallest part could be red or blue. Now we just have red. And there is a lot of low-hanging fruit for this S1 of Q. So I'm expanding the series out to 50 terms. The series that was on the screen, I'm using Maxima, which is the granddaddy of all computer algebra packages. And so for someone my age, is quite a natural thing to use. And so this turns out not to be in the OAIS, but it's a rather interesting series in that at first glance you see most of the terms are even. Most of the coefficients are even. Well, of course, there's the zero term, the Q term. They're odd at Q, Q cubed, Q6, Q10, Q15, Q21, Q28, Q36. So it looks like the coefficients are odd, where the exponent of Q is a triangular number, and every other coefficient is not only even, it looks like they're all divisible by 4. And what we're going to show is precisely that this is true. So here's the generating function. Now, the trick is that 1 minus x quantity squared is congruent to 1 plus x quantity squared mod 4. So I can drop that minus sign in the infinite product in the series, getting it back to this. And this is a famous identity that follows from the classic Heine transformation. And now you see mod 4, that the S1 is indeed congruent to this, so that every term is divisible by 4, except where you have the triangular numbers where it's obviously odd. But there's even more going on here. There is a relationship between S1 of Q and our original generating function for PD of n, namely the square of this infinite product, 1 plus Q squared, etc. Namely, it's multiplied by this. Well, it's not Euler's pentagonal number series because the signs are wrong, but otherwise it's all the same exponents. It's just that the signs are different. And then there's this correction term, which is Gauss's series again, except that the signs again are wrong there as well. So this takes a little more effort to prove. It's a little more down in the weeds, but it's such a beautiful result that I want to describe it for you. The aficionados, I hope, will be able to follow the proof, but basically it's the style of proof that Ramanujan used extensively in his Lost Notebook. Well, not only is it style of proof, I'm going to quote directly from the Lost Notebook, where Ramanujan has an identity of this nature, and you set A equal 1 multiplied by minus q infinity squared, and bingo, you have this theorem. So you have this now, this relationship with the classical theorem. Well, all this is very natural, as so far as with all good mysteries, everything seems to be in place. Nothing much is happening, few sort of elegant results that really were embedded in the Lost Notebook, although Ramanujan never commented on the combinatorics of his discoveries. So the combinatorial applications are all new. So let's look at S1 of Q a little more closely. And this time we will apply the Heine type methods that Ramanujan also applied so terribly successfully. So we rewrite this series this way. And now I'm going to alter the term in two parts. So the q to the n remains, but I've introduced this factor q sub n in both numerator and denominator, and I've amalgamated it with one of the minus q sub n's to give me this expression. And now I'm just replacing the quotient of the final two Q Pockhammer symbols by infinite products. And once you cancel everything out, you'll get back to the previous line. But those infinite products, that quotient of infinite products, expands by the classical Q binomial theorem, so that we get this double sum. And now the outer sum on n can actually be summed. And we have this inner sum. And now the problem with this inner sum is the infinite product in the denominator, which involves q to the m plus 1. And so the behavior of that product intimately depends on whether m is odd or even. So we need to split that sum up into the cases where m is even and m is odd, and then we can simplify this as follows. Namely, we bring out the infinite product in each case, do relevant cancellations, and you have Ramanujan's psi function, which is just the Gauss triangular number series, times this first sum and this second sum, which I'm going to designate by psi of q times the even term t sub e of q, and this minus 1 q sub 2n plus 1, I'm going to bring the 1 plus 1 out front as a 2 and call the rest of it t0 of q. So if I look at the t even q term, you see this infinite series, which if I multiply by q infinity, as I do at the bottom of the screen, lo and behold, it's this series, which is, again, the pentagonal number series, just with, this isn't Euler's series again because the signs are wrong, but the exponents are the pentagonal numbers. And so the first thing we'd like to do is to see if this is actually true. Well, this is, again, semi-low-hanging fruit. T sub e, you can rewrite what I had back there as this 2 phi 1, the classical Q hypergeometric series, which transforms by Heine's transformation. And when you simplify it, you wind up with the T of Q equal this expression you see now, which is quite simple. And fortunately, there it is in Ramanujan's Lost Notebook. So far, I've had to do nothing clever except get things reduced to a sort of minimal form. And lo and behold, Ramanujan pitches in to get us exactly the expression that we had hoped for. And so now we get to some of the mystery. So we've dealt with, this was dealing with TE, and TE, you see, is evaluated in this very lovely way. Basically, it's this 1 over this infinite product times that series. But here's TO. And so the first thing you ever always do or I always do, and then running into a new series like this, which seems to have some significant interest, is to go to the OEIS and ask it, what's happening? And A344650 in the OEIS tells us this is the generating function for odd length partitions of 2n with distinct parts. You get exactly the same series, which seems incredible in that that series at the top of the screen seems not at all what it should be if it's going to generate this. But as we will see, we move on and the terms are different starting at 14. So what's going on? We need the generating function for partitions of n into odd number of distinct parts in order to see what its relationship is with this TO of Q. All right, so hopefully EA344650, which I just looked up, has it, or at least has a link to it. Well, here it is. And you go searching frantically for a link. Here's the first page of it. Here's the second page. You probably can't read much of it, but what you can see is that it has a few formulas in terms of Maple programs and mathematical programs, and it has relations to all sorts of other the sequences in the OEIS, but there is no generating function. So we have to go after a generating function. So how do I get odd length partitions of partitions into distinct parts? So you take every other term in the generating series for partitions into distinct parts. So in the second line, you can see the generating series for partitioned into distinct parts, where I've introduced this factor 1/2 times 1 minus 1 is minus 1 to the n. That kills out all the even number terms and leaves me with the odd number terms. And then I can sum the series, as you see in the third line, and do use Euler's identity for minus q infinity, which is 1 over q squared infinity. And I can split the infinite product q infinity into two infinite products, as you see there. And I carried out fully to get the even terms. I have to 1/2 PDO of Q plus PDO of minus Q. So I have to put all this stuff together. Then I just do manipulations of the infinite products to get this set of factors. And so to take these factors one at a time, here's the first factor. And I'm rewriting things so that I can get to Jacobi's triple product, which expands this way. And the first factor is given at the bottom of the screen. It's basically this theta series with this infinite product out front. Here's the second factor. Well, it has a minus sign involved. So now I factor out the first infinite product, and the infinite product inside the parentheses is another example of one of the famous Jacobi identities. And so it becomes this 1 minus this. And of course, now you combine the terms n and minus n, and the 1/2 then drops out. The zero term disappears, and this is what you have. So you now have the second thing. So if you put these two factors all back together and replace q squared with q, then you find that this generating function for this entry in the OEIS is 1 over the standard Euler infinite product. And now you have the first factor is a full theta series, and the second factor is half a classic theta series. And so if you expand it out, this is what that looks like. Well, if we expand q infinity, see, we have the PDO of 2n q to the n. If we multiply by q infinity, we get q6 minus q7, q12, q14. If we multiply that times TO of Q, we get Q, Q6, Q7, minus Q7, Q12, Q15. In other words, the discrepancy arises back where the mystery was most vivid because basically it's there's the Q to the 14 in this series and the Q to the 15 in this series. But looking at this is highly lacunary. It's not as lacunary as an ordinary theta series where there are only about the square root of n terms. But I've taken this out to 300, and these are the only non-zero terms in this sequence. So we have one mystery explained and another one arises. What is this anyway? So in order to understand this, we have to recall that we already proved this is the identity we proved for S1 of Q. And so what we have is that S1 of Q, from the first theorem we had, remember we related S1 of Q to the full generating function for partitions into two colors and distinct parts. And we had that lovely thing that followed from Ramanujan's work. And we also know what the TE of Q is. And so we would need to multiply psi of Q times TE of Q. And we will have a formula then for TO of Q in terms of the series that you'll see on the screen. So hence 2TO of Q is this. And so 2TO of Q, wait a minute, that was, so the expression at the bottom of the screen is the one that follows from putting all of this together, and it, if you look at it carefully, you see that the two expressions are basically all the exponents are identical. The only thing funny going on here is that in the top row, there's minus ones to the n's inserted in the sums that disappear in the bottom row. So let me illustrate this with this. This is what's going on here. We have multiplication of the other two infinite series where you have alternating terms in the first product and no alternating terms in the second row. And so there's lots of cancellation that occurs precisely when you have parity as being the same for both the A and the B. And so you wind up with the fact that this is the expression you saw in the previous slide simplifies to this. And so here's the theorem that TO of Q is equal to this expression, and this simplifies down to precisely this, which is precisely the situation that we saw before. And now you will see the explanation of this semi-lacunarity because you have basically these theta series that are multiplied together to give this expression, which has so very few terms and such very small coefficients. Out to 300, there are only just a few terms that have a coefficient as large as 2. All the rest are minus 1 or 0. And this is why that is the case. So I have, I think I am missing a slide here. So just let me check my notes a moment because I'd be sorry to miss it. So There is one last mystery after this, namely, we've now at least explained the relationship of these Q series to the series in the OAIS, but that mystery then means that we really have no combinatorial explanation of either TO of Q or in any way that is partition theoretic. And so one last mystery remains. The question is, are there any partition identities lurking within the confines of this narrative? And the answer is yes. And this will be relating to the these last functions that we saw. Let A of n denote the number of partitions of n in which the first integer missing as a part among the numbers 0, 2, 3, mod 0, 2, or 3 mod 4 is congruent to 3 mod 4. So this is like the MEX, the missing excludant, except that we don't pay any attention to numbers congruent to 1 mod 4. They can appear or not appear. We don't care, but we are looking for among numbers that are the other numbers 0, 2, or 3 mod 4, and we are only looking at those first partitions where the first missing integer among those three congruence classes is congruent to 3 mod 4. On the other hand, we let B of n denote the number of overpartitions of n in which the largest part is even and not overlined. So the largest part is even and not overlined. The other even parts may be overlined, and the odd parts are distinct and not overlined. Okay, so theorem for n greater than or equal to 0, A of n equals B of n. And how do we prove that? So what we're going to look at is the generating, back to this TE of Q, only we're going to take off the constant term. So we're having n greater than or equal to 1. And so that we have the largest part is even and not overlined. So that's Q to the 2n. The odd parts have to be distinct, and the other even parts may or may not be overlined. And the Q squared Q code sub n generates, how did that happen? Generates the other even parts that aren't overlined, and this is clearly B of n. On the other hand, TE of Q is equal to this. And therefore, TE of Q minus 1 over 2 is we've already proved that this identity is true. And so now you see that what one has is the in order to, excuse me, I'm sorry. All right. So basically, you see the minus 1 at the end of the first line. You multiply numerator, you multiply by q infinity, so you can factor the q infinity out, and that produces the genuine pentagonal number series that you see on the second line. And now these terms, some of these terms cancel, and you're left with the expression you see there. And 6n squared plus 7n plus 2 is the sum of the numbers that I talked about earlier, namely the 2, 3, and 0 mod 4, all the way up to 4n plus 2, with 4n plus 3 missing. And that is the A of n that you see at the bottom of the screen. And that is precisely the same thing that we saw before. So basically, I had the choice of either trying to squeeze this into 25 minutes or saying that I would take 50 minutes. And so this I have a few more things to say. Namely, there have been several papers that are following up on this. The most recent one is by Ankush Goswami, a former student of Krishna's, who has gone all the way back to, sorry, here we go. It's gone all the way back to this, where the theorem is that this is congruent to 0 mod 4. Obviously, this is a very natural combinatorial question, that why is everything except for the triangular number divisible by 4? And Ankush has written a beautiful paper in which that mystery is solved. And as I recall, and he has very other nice results as well. So anyway, there is a lot going on here. Bahrawi and I are following up on this because there are much more subtle aspects of this. As many of you know, the rank generating function is closely related to Mach theta functions. There's basically a parallel theory to Mach theta functions and false theta functions, and Bahrawi and I are pursuing that as well. And so all I close with is elementary, my dear Watson. Thank you very much for your attention. And I'm open to questions.
Thank you, George. Any questions for Professor Andrews?
Yes. Maybe hi, George. This is Vlad Verbitkin speaking. Do you have a definition for semi-lacunary? Or is it just your
not so basically I would say that semi-lacunary is obviously a loose term. So my idea of lacunary is that the number of non-zero coefficients is little o of n as you go through first n coefficients. And so, but basically, in the classical theta series, it would be big O of the square root of n, essentially, and this is much closer to. There are many more coefficients here than just going out to the square root.
Any other questions? So I have one.
Yes.
George. So for partitions into distinct parts,
yes,
generating function minus q infinity,
yes,
almost all coefficients are even. That's
yes,
your pentagonal numbers theorem.
yes.
And actually, almost all coefficients are multiples of 4. Almost all are multiples of 8, and so on, and almost all are multiples of any given power of 2.
And Gordon's established that.
Yeah. Now, for your minus q whole squared, minus q infinity squared, you have shown that everything is almost all are multiples of 4. What about higher powers of 2?
Yes, excellent question. I don't know the answer. I've not even thought about it. So it's obviously grist for the mill. Of course, what Ono and Gordon had going for them is the fact that the modularity of that generating function. This is definitely closely tied up with the classic false theta function, but that doesn't mean that there may well that doesn't. All it means is it's going to be a harder problem, but and there may be something there. I don't know. I have not looked. That's an excellent question.
Thank you. So no more questions. Let's thank Professor Andrews. Switch it up. Okay. So maybe we can start the problem session in 10 minutes instead of waiting until 5, if you all are okay with it. Okay. So I'll just give it